Hello my dear students, and once again welcome back to the Chem School. Now if you remember, we have covered something called as Markonikov's rule, and today we are going to cover Anti-Markonikov's rule. So we'll talk about everything in detail. So let's get started. Now if you remember, when we spoke about Markonikov rule, we said that for Markonikov rule we need something called as unsymmetrical alkene and unsymmetrical reagent. This criteria remains the same even for Anti-Markonikov rule. Okay, so this can be applied only to unsymmetrical alkene, and it can be applied only with HBr, not with any other unsymmetrical reagent. Okay, so remember that this is the most important part, that you will not get an Anti-Markonikov rule with any other reagent. You will get it only with HBr. That is very specific. That too, the other specification is you will get it in presence of peroxide or some radical initiators. Okay, so in this case, remember, Anti-Markonikov rule, you should have unsymmetrical alkene, you should have HBr as the only reagent in presence of peroxide. Then what will happen? Then what will happen is, in Markonikov, what happened is H goes to the carbon with more number of hydrogen, right? I repeat, H goes to the carbon with more number of hydrogen in Markonikovs. Now we are talking about Anti-Markonikov. So what should happen? The opposite. Anti means opposite. So H should go, the proton should go to the carbon with less number of hydrogen. Straightforward. Okay, so let's understand it that way. So what is going to be your product? The product is going to be, you will write down CH3. When the proton goes to the carbon with less number of hydrogen, here you will get CH2. Obviously the Br will go to the carbon with more number of hydrogen, and what you will get is CH2Br. We will understand this particular phenomena with respect to mechanism, okay, and examples. So when you understand the mechanism, it is going to be very clear why this is happening. Okay, so as of now, Anti-Markonikov rule in presence of unsymmetrical reagent, that is only HBr, unsymmetrical alkene, and in presence of peroxide, the H will go to the carbon with less number of hydrogen. Khatam. Okay, it is nothing more than that. Fine. So this is what you get your product, that is 1-bromopropane. Is this clear? The other thing that you should remember is, because this reaction is happening in presence of peroxide, it is also called as peroxide effect. Okay, now this particular effect is also called as Kharash effect or Kharash effect, whatever you would like to say. Okay, fine. So the other name for Anti-Markonikovs is peroxide effect or Kharash effect. Is this clear? I hope this is very clear to all of you. So now let's understand the mechanism for this particular reaction. Okay, now we said that Anti-Markonikov takes place in presence of peroxide. So whenever you have this, OO linkage, right, you will say O single bond O linkage, then you will say it is a peroxide. So this is a particular in general peroxide that we have taken. Okay, the next thing is, you should remember that when you talk about Markonikov, that was electrophilic addition reaction. Okay, I repeat, that was electrophilic addition reaction. But when you talk about Anti-Markonikov, this is a radical reaction. Okay, this is a radical addition reaction. Why it is a radical addition reaction, we will understand in short. Okay, now let's start. Now whenever you talk about radical mechanism, you have standard steps. That is, you will first generate the radical, which is called as radical initiation. Then the generated radical will react with your major reactant. Okay, that is called as radical propagation. And at the end, what will happen? All the radicals will react with each of them. Okay, and there will be no more radical left in the reaction. That is called as radical termination. So let's start with radical initiation. So for radical initiation, you will take the peroxide. So in this step, that is first step, radical initiation step, what will happen? The peroxide, if you can see, it is symmetrical. Okay, and because you said radical reaction, radical mechanism, then you should have some energy to generate the radical. So we use UV source, that is UV light. Okay, so whenever you have UV light and you have this compound, you can see that this compound is symmetrical. So for symmetrical compound, which type of fission do you have? You have homolytic fission. So break the bond symmetrically. So when you break the bond symmetrically, you will have homolytic fission to give you this particular radicals. Now, how will the radical look like? You will get RO. You can see that the bond is breaking into half. This oxygen will take 1 electron and this oxygen will take 1 electron. So you will get 2 OR radicals. I repeat, you will get 2 OR free radicals. Is this clear? So these are your alkoxy free radicals. Next, what will happen? This free radical that is generated will react with HBr. Okay. So the generated free radical is now reacting with what? It is reacting with HBr. So when it reacts with HBr, what will happen? Now this has to become stable. Okay. So what this will do? This will now react with this H. Okay. So OR will react with this H to give you what? To give you ROH. So that is your byproduct, that is alcohol, which is very stable, so it will remain in the system. The next thing what you will have is, okay, you will have this Br generated, that is Br free radical. Okay, now you can also get esters, and depending upon what are the different peroxides that you have used, so you need not worry about this. Okay, as of now, this is what we are going to write. It looks like alcohol, but it is not an alcohol. Why? I'll tell you later. Okay, so in this case, what will happen? Br will also take 1 electron and generate Br free radical. Now this is important for us, okay, because this Br radical, this bromide free radical will go in the next step, that is propagation. So in propagation, what will happen? Let's change the pen. So in propagation, what will happen? You will take the propene, okay, and react it with Br, that is bromide free radical. Now, what are the choices that you have? Where will the Br go? The Br can go over here. It can also go over here. So as of now, let's consider both the options. Okay. So what will happen is, when the pi bond breaks, this carbon will take 1 free radical or 1 electron, and this carbon will take 1 electron. Okay, so the Br can go at either side. The Br can react with this carbon, or it can react with this carbon to form a bond, to form a sigma bond. Okay, so let's consider both the options that is going to happen over here. Okay, if the Br goes at this place, how will your intermediate look like? You will get CH3, then you will get CH, then the pi bond was broken, right? So you will get single bond, then you have CH2Br, right? But this 1 electron will end up on this carbon, generating a free radical on this carbon. So because it has a radical, that is the reason I said this is an intermediate. What is the other intermediate possible? The other intermediate is, you will get CH3. We said if the Br goes over here, then you will get CHBr, okay, and you will get free radical on this particular carbon. Now don't forget about the stability of intermediate. Here you know that you have free radicals generated. Which type of free radical is more stable? Let's talk about the type of carbon that you have. This carbon is attached to 2 different carbons, therefore this is a secondary carbon. Therefore this is secondary free radical. That's correct. The second one, the second intermediate that you have, this is connected to only 1 carbon. Therefore this carbon is primary. Therefore the free radical is also primary free radical. Now recall the stability of radicals. Okay, so when you talk about stability of free radicals, you must never forget that tertiary free radical is more stable than secondary, and the primary is least stable. So now here lies your mechanism, most important part, that because you have a secondary free radical generated at this particular site, the Br is going to your primary carbon, and therefore now this particular thing will react with the other thing to give you nothing but this particular compound. Okay, so this is what you should remember. What happens is, because the radical generated, the intermediate generated is more stable, therefore you will get this as your major product. There are other reasons involved. We'll talk about that later. I hope this is very clear to all of you. So this explains most of the part. Now let's take the final step. So in the last step, what we will do? we know that this is important, so we will take this particular intermediate. Okay, so just take that. So you have CH3, then you have CH with the free radical, CH2Br. This will react with HBr. The HBr is your reagent, so that is going to be in excess. Okay, so when you use HBr, what will happen? Now you know that this is organic chemistry, and apart from that, carbon has more affinity to hydrogen. Okay, so in this case, what will happen? This carbon free radical will now try to react with this H. Okay, and again Br free radical is generated. What will Br free radical do? Again, it will carry out similar type of reactions. So that is not a concern. Okay, let's make the product now. So what you will get is, you will get CH3, you will get CH1, H was already there, the other H is coming into picture. So you get CH2, and then you will get CH2Br. And a new bromide free radical is generated. So now you can see that you have already obtained the product that was desired, isn't it? Right? So here we will not talk about termination, because as of now it is not very important for us. But you can see this is how the mechanism for anti-Markonikov rule goes. I hope that you don't have any other doubt with respect to this. Okay? Practice the mechanisms at least 2 or 3 times to understand the concept in detail. Now let's understand few more details in anti-Markonikov rule. Now, if you remember, we said that we will use some different types of peroxides. Now, this is one of them, which is most common. Okay. Now, this is benzoyl. This is benzoyl group, and in between you have an oxygen. So this is called as benzoyl peroxide. I repeat, most of the time you will see in organic chemistry, this is the peroxide that they use, which is called as benzoyl peroxide. Now, no one will write this big structure again and again. So usually you will see this written as C6H5CO carbonyl group. You can see that this is twice. So you will put this as twice, and you have this oxygen outside, which is only once. Okay. So most of the time if you see something written like that, it means it is nothing but benzoyl peroxide. You can also use H2O2 over here. That is hydrogen peroxide. Peroxide should not be a problem. Okay. So again, this will give you your final or desired product, which is CH3, CH2 and CH2Br. Now what we need to understand over here is why only HBr is used for anti-Markonikovs, or why only HBr shows anti-Markonikov rule and other reagents does not. Like what? Now if you talk about this Cbr bond formation, okay, consider that you have used other halogen reagents. Let's say, we'll talk over here. Let's say if you use HF, okay, you will get CF formation. Okay, so if you use HF over here, the product that will be formed, let's say it is going to be CF. Okay, similarly if you use HCl, you will get CCl bond formation. If you use HBr, you can see now you have CBr formation, that is carbon and bromine bond formation, right? And if you use HI, you will get CI formation. Okay, so if you use this reagent, this is the bond that will be formed in your product. Okay, now what happens? See, the thing or the problem is HF bond is very, very difficult to break. Okay, so the bond dissociation energy is very, very high, right? You are supplying energy to break this HF bond. So that step is going to be endothermic, right? The next thing, when CF bond is formed, that much energy is not released. Okay, so in this case what happens, compared to this particular bond formation is going to be less stable. So HF will not break to give you CF bond so easily. That is going to be a completely different mechanism or completely different reactions. Okay, so that is the reason this has gone into picture. And you know that we don't talk about use of HF so much in organic chemistry. The next thing is HCl. In HCl, again, what will happen? The HCl bond breaking will take more energy. So that is going to be endothermic. While the CCl bond formation, okay, in that case, you will not have that much energy released. So the net energy is going to be positive. It means the net energy is positive. It means the step becomes endothermic. Clear? Right? But what happens with HBr? In case of HBr, okay, the bond is broken automatically and the energy is released. It means that in this case, if you use UV light, the bond is going to break. It means this step is going to be partially exothermic, okay? And more energy is released when this Cbr bond is formed. It is highly exothermic, okay? So this particular step calls everything, okay? This step is highly exothermic, okay? And that is the reason this particular reaction comes into picture, okay? What is the problem with HI? With HI is also the same thing, okay? HI bond will break easily because the bond length is quite large, okay? But what happened after that? Ci bond formation does not come into picture so easily. What happens is I free radicals, okay, react with I free radicals to give you iodine. Is this clear? So iodine is subliminary solid, so you can write down it is solid and gaseous. So you will get this particular thing, that is you will get iodine formation. Okay, so now what do you have left to give this type of reaction the best? That is nothing but HBr. I hope this is clear. So in simple terms, what is happening is a very large amount of energy is getting released. It is highly exothermic process when your Cbr bond is getting formed, and that is the reason that you study this as Markonikov, or sorry, as anti-Markonikov rule. So I hope you don't have any doubt with respect to this. Okay. So let's recall anti-Markonikov rules once again. So what we said is for anti-Markonikov, we will use unsymmetrical alkene. We will use unsymmetrical reagent, only HBr. Why? I hope the reason is very clear. Okay. The next thing, in presence of peroxide, you will get this particular product. That is, the H will go to the carbon with less number of hydrogen. I hope this is very clear. And one more thing, in the next class, okay, or in the next video, I'm going to come up with a comparison of anti-Markonikov and Markonikov rule. So do watch it out. Okay. See you soon in the next class. Thank you.